Yo, I'm gonna ask you a question. Alright, I know I've been asking you a lot of questions these days, but just bear with me, alright? Bear with me. Just stay here for a while. Alright, I want you guys to listen to this very intellectual question. Alright, let's say I'm pooping over here. Toilet bowl. Right? I'm over here pooping. Okay, that's just drawn so bad. Forgive me, guys. Okay, wait, what? Okay, whatever. You get my point. You get my point. I'm pooping over here. Alright? Heaving a sigh of relief. And then, you are over there. Okay? Over there. It's your nose. And then you're like, this stinky smell starts traveling into your nose, and you're like, hey, wait a second, what's the smell? And after you start dying from the such, it's so stinky, right? You start dying. Let me ask you. I looked over here. All the stinkiness is over here. Why do I smell it here? So I've got a question for you. Interesting question. I'm pooping over here. All the smells are here, but somehow I can smell it from here. Why? And a lot of people will tell me this answer. The smell spread, use the word spread, from the toilet bowl to your nose. Okay, and a lot of people will be like, Hiya, what in the world? They will say this is such a stupid question, right? It's just the smell from here, smells in your nose. Easy, that's it, period. Nothing to say. Why do you need to like always make a mountain out of a molehill? There's nothing much to say. Why are you asking me this kind of stupid questions? Well, you probably won't believe, but there's actually more than what meets the eye. You may just think the smell spreads, but exactly how, you don't know. And today, I will be telling you something, a concept very important. Okay? It's called difference. Just kidding. No, don't call it difference. We call it diffusion. Okay, you may be like, what in the world is diffusion? Big words right here, but it's actually quite simple. So let's learn diffusion. Okay, it's a scientific topic, alright? Expand your knowledge, come on. Alright, so, now, here's the thing. I'm just gonna give you a super easy example, alright? A bottle of perfume over here. Right? I have a bottle of perfume over here. And then, I go ahead and spray these into the air. You're over here. Your nose is here. For some reason, you manage to smell the perfume. Why? So, now, these, I'm just going to sort of call it the perfume molecules. There are these small particles, perfume molecules. How do they move from here to here? Now, as we all know in the kinetic particle model, these things, they are sort of like particles, right? Particles. So, the perfume molecules from here, they spread to here. How do you do that? And I want you guys to think about it. Pause the video and think about it. Alright, don't tell me stuff like, oh, they just spread over there. So smart. No. So, now, let me zoom in for you. I'm gonna do something called zooming in. Look at this. Zoom in. I'm gonna zoom in for you. Zoom in. Zoom in. I mean, look carefully, guys. Zoom in. Zoom in. Zoom in. Zoom in. Zoom in. Zoom in. Look at this. These are the perfume molecules, the small particles that you don't see. Now, I'm pretty sure we can all agree. I'm pretty sure I've reiterated this so much in previous videos on how molecules move. They bounce around. So, they move randomly, they move continuously. That's why you should know molecules and you all do that. Okay, so this is little molecule number 1. Now, when the perfume is sprayed, alright, When a perfume is sprayed, okay, let me just draw it up for y'all. Oh, sorry, wrong color. The perfume is sprayed. These are the perfume molecules. Now, if you're gonna go over here, which is where your nose is, there's gonna be nothing. You're gonna see absolutely no perfume molecules over here. You can see absolutely no perfume molecules over here. Yeah, but here's the thing. Over here, these perfume molecules. This is perfume molecule 1. Agree that it's gonna be moving randomly. So it's gonna move here. Right? Point, 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 point. Now, here is what this is the zone where there's a lot of molecules. The zone what I call the high concentration. And I don't call it myself, right? It's really defined as high concentration. The zone of high concentration. And you should be concentrating on this lesson right now. So if you're scrolling through TikToks, you better look at this. High concentration. Okay, so this is the place of high concentration where there's a lot of molecules that are all crowded, alright? And of course, this place with nothing is called low concentration, which is probably what's going on in your mind right now. Low concentration, so better lock in. Low concentration right here. This is high concentration, this is low concentration. You can see there's so much. This one, there's nothing, it's practically nothing. So, now, let me ask you a question. Do you agree that these molecules will slowly start to drift over here after some time? Right? Now, but some of you may say, yo, but didn't you say that molecules, they move continuously and randomly? Randomly. So they won't purposely just try to drift to a place with lower concentration. Yes, that's true. I said that molecules move continuously and randomly. So they won't be like focused on moving from this direction from point A to point B. They will just move in any direction they possibly want. And they won't be inclined, alright? They won't have any biasness to be purposely deliberately trying to move over to places with lower concentration. But why do they still do that? Now the reason is because, think about it. If you're in a crowded area, there will be a lot of bouncing off. You will see a lot of like molecules just hitting against each other, colliding against each other, boing, boing, right? You will just hit everywhere, boing, boing, back to this place, boing, boing, back to this, boing, over here. There will be a lot of molecules just crashing against each other, as you can see, right? Because they're all together. So they will inevitably, some of them will just boing all the way to this place with nothing, absolutely nothing. Oh, nothing is gonna boing back, right? Just think about it this way. Right? If you're in a room full of balls, and these balls are super bouncy, right? They're super bouncy. You take these balls, alright? Let me give you an analogy. You're this room, okay? This is gonna be the place with high concentration. This is gonna be the place with low concentration. Wait, sorry. My stylus ran off ink. Okay, I'm gonna have to use my hand. Low concentration. Alright, so high concentration, low concentration. I'm gonna throw in a bunch of balls over here. A bunch of super bouncy balls that will hit against each other, bounce against each other, ricochet around. Now, agree that these balls, they will just be bouncing off against each other. But inevitably, some of them will just like, the path will be like hit here and over here, hit here, here. And like, come on, right? They move randomly, but even if they, okay, here's the thing, they move randomly, right? So there's a 50% chance that they will move to the place of low concentration, and a 50% chance that they will still remain in the high concentration place. Like technically, there's a 50% chance that they move to low concentration place, 50% chance that they'll still remain in high concentration. So let's say that they remain in high concentration, but they will still hit against other balls, and slowly they'll just slowly get pushed because they'll be like, it's so crowded over here, and they'll be like, and they'll suddenly just suddenly just pump over all the way over here. They'll be like, and suddenly get just like completely hurt over there, catapulted over there, and then this is a low concentration place. Cool. So that is why, although molecules, they do really move continuously and randomly. But this randomness is actually part and parcel of what makes them move to places of low concentration. Because firstly, 50% of it will just move to low concentration, first and foremost. And second and foremost, yeah, there's also quite foremost. If let's say they decide to stay in high concentration, they will still hit against each other and slowly they'll just get pushed over there because they realize this thing is so crowded and it feels like a wall, a barrier that they really can't cross, and they slowly just like hit this barrier and just push over there. Right? Think about it. If there are gonna be so many balls, right? There's so many balls in this high concentration place that they may just form this big wall, or they will just form this thing that's very hard to just even move past. And anything that comes over here will just bounce right off, like so. So that is why, although we say move continuously and randomly, right, they will still inevitably drift over to the low concentration, although that was not their main intention, right? So let's go into this thing. Perfume, I spray it. Okay, we zoom in. That's actually perfume molecules, but if we zoom in, what we are actually dealing with are these small little particles that are just moving continuously and randomly. And they slowly, as I've explained later, they slowly will go to places of low concentration where there's no molecules. And they will just enter your nose. Now, so messy. Now, here's the definition. I know it's a bit, my handwriting's a bit atrocious because I have no stylus now. Okay, but just copy it out. Diffusion is where particles move randomly. Okay, because they do. We all know that. From a region. Oh my god, why is it so hard to write? Okay, so diffusion is where particles move randomly from a region of higher concentration to a lower concentration, alright? I don't have a stylus right now, that's why I'm just lazy. I just write con, but write concentration now, please. So get what I'm trying to say? So diffusion is the high concentration part, like too bouncy, so many molecules over here. Slowly, let's move over to the low concentration and then go and enter your nose, right? Then you smell all the stuff. Okay? So of course the verb is diffuse. So you can just say that the particles they move, the molecules they move from a region of high concentration and they start spreading out through the room, they diffuse into your nose to the place with low concentration or to your nose, whichever whatever you're trying to answer. Okay, so you get what I'm trying to say? Alright, now let me give you a very easy example. This one was a bit more casual, but I'll give you a more scientific example of diffusion. Okay, so we can use bromine vapor. Okay, just for your knowledge, bromine is like a reddish brown liquid lah. Okay, and but it can evaporate very easily, and then it will form this reddish brown vapor, which is called bromine vapor. So over here, this is air. This is bromine vapor. And please do not try this at home. What do I mean? Please do not handle bromine vapor because bromine vapor is harmful unless you're like very big brain and you know how to do it. Okay. Okay. So bromine vapor, air. Okay. So this bromine vapor will just slowly just spread into this remaining place. Bromine vapor is only placed here, but for some reason it will go over here because it diffuses, right? The high concentration, the particles, the bromine vapor particles are like so crowded and they and boom over to the low concentration with the air. Okay, now you may think that diffusion just happens in gases. Diffusion only happens in gases, but just like Brownian motion, diffusion also happens in liquids, but it's much slower lah. Okay, so usually I just talk about diffusion in gases, but it can also happen in liquid. So I'll give you an example. So if you take potassium manganate, okay, you take potassium manganate and you place it in water. Okay, first things first. This is H2O, your water. You take your potassium manganate, you just throw it inside. Now, you take one crystal of potassium manganate, alright? So it should be like a one single crystal, like this, one single little block crystal. Okay, so now these molecules, they aren't like bromine vapor. We know bromine vapor is a gas, right? We know bromine vapor is a gas. So we don't need to do much. The gas particles should just move all over. Okay. But here's the thing. Unlike bromine vapor, which is a gas and is very straightforward, just diffuse over there. Potassium manganate is one single crystal. It's a solid. And solids cannot diffuse. Solids are just one single thing, right? You won't see a solid trying to diffuse, right? So usually when we talk about diffusion, it's usually a gas diffusing. It's like bromine vapor or some smell, like some molecule diffusing. Solids, do you think this one single crystal will be able to diffuse? No, right? This one is easy because it's bromine vapor, it's gas already, so you can just straight away diffuse. But this potassium manganate, one tiny crystal, is not a gas, it can't do anything. So firstly, it's going to dissolve in water because it is soluble in water. So this crystal of potassium manganate will dissolve in water and it will form this little purple solution. That's why I use the color purple. It will form this little purple solution, right, as it dissolves in the water and sort of liquidy down. And then this purple color will spread through the water. It will spread through this water. And this is, of course, clearly through diffusion. Diffusion. Okay? So, the purple particles, they diffuse through a liquid. Alright, now, before the lesson ends, I'm going to just tell you one more quick thing that you need to know. Rate of diffusion. So, how fast does it diffuse? Now, of course, it depends on what is diffusing, right? But most importantly, there are two factors for rate of diffusion. Firstly, is the temperature of the gas. The temperature of the gas. So now think about it. Guys, think about it. We all know that gases. Okay. Explain one more time. So sad. Okay. I know this is like the 1 millionth time I'm drawing this. As you've seen from previous videos, if you did. Sorry, this has to be expressed in green. I'll just do one more time. Okay, so you all know solid, liquid, gas. I don't even care about the colors at this point. Now, you know that solid, you heat it up, you get liquid. Liquid, you heat it up, you get gas. Agree? We all know this concept. Solid, you heat it up, you get liquid. This is melting, and this is evaporation. Okay, basic knowledge, huh? Now, think about it, guys. Temperature of gas. We can clearly see that the more you heat it up, as you slowly heat it up, from solid to liquid, you heat it up. You can see that the heat will slowly cause these particles to move away. Again, liquid to gas. Heat up, heat up, heat up. And as it heats up more to a gas, from liquid to a gas, it will become super far apart. Right? Because these particles, as they're being heated up, they gain kinetic energy. They start to vibrate, right? Alright, and then once they reach for example, the melting point, the boiling point, they will have enough potential energy to overcome these strong intermolecular forces that is between them, and boom, they separate. So you can obviously see a temperature of gas. The higher the temperature, the more vibraty it becomes. It's not a real word, but the more vibraty it becomes. So of course, if it's more vibraty, it will have a faster diffusion, agree? So, first concept that you need to learn. Okay? For rate of diffusion, First concept for diffusion. Okay, first concept for diffusion. Sorry. Okay. Higher temperature, higher the diffusion. Now the other one is the molecular mass of the gases. Now, basically it sort of means like how heavy these gases that are trying to diffuse are. Now think about it, if you have a little small scrawny boy who is running, right? You probably think that he'll be running faster than a big fat boy, right? So if you have a small little scrawny boy, right, vs a big fat boy, who do you think will run faster? You probably think the small scrawny boy can run faster, right? Because it's more like sort of like agile, sort of. Now, I want you guys to use the same logic for these molecules. If the molecules are smaller, if the molecules are lighter, they will be able to move faster, right? Because they have to carry less weight, sort of, right? So these molecules, if they're smaller than a small scrawny boy, they're small, they can move faster. Agree? They can move faster. And they move faster, that means faster diffusion. So this one is smaller mass, faster diffusion. Right, so that's it for today's video. Thank you very much for watching, or I shouldn't have done that, okay, but you get what I'm trying to say? Sorry, if you guys want to see accidentally, just scribble on the page. So thank you guys for watching. Please like and subscribe and comment down if you have any questions. Alright. Oh yeah, just so you guys know, right, these two things, right, they affect diffusion, they affect the rate of diffusion, right? But they also affect Brownian motion. It's not the same, because if you think about it, they're sort of related, right? And both Brownian motion and diffusion, they have sort of like proved the kinetic particle model that they have proved molecular motion. Diffusion has proved that there are really molecules in the air. That's why they can, like blah 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 blah, and then drift over there. Like they collide with each other and then move over there. So that's why they both prove molecular motion, Brownian motion, and diffusion. So they're sort of related. So these two characteristics, these two things, they also affect Brownian motion. Alright, so yeah. Okay, so it affects Brownian motion, it also affects diffusion. Okay, so these two take note that they affect Brownian motion and also diffusion. Okay, so guys, thank you very much for watching. I really appreciate your time here, right? If you managed to stick all the way up to the 23-minute mark without skipping whatsoever, okay, but if you did skip, hope you actually learned something. Okay, so thank you very much. If you have any questions, you can comment down below, share with your friends. Alright, they need to learn as well, right? They need to be, grow your brain, right? Grow your brain. But if you don't already know, just try to recap, try to clarify any doubts you have. That's also good as well. Alright, you can comment down below. Alright, if you have anything you want to ask me, or just want to say, oh, it's a good video, you want to compliment me. Thank you very much. I am flattered. Alright, so like and subscribe if you like this video. Thank you very much. Peace.